to the fifth lecture on diffusion mass transfer, which is module 1. This lecture we will cover the steady state molecular diffusion through variable area. Before going to this lecture, let us have a quick recap on our previous lecture. In the previous lecture, we have considered steady state molecular diffusion through constant area. Constant area. Here we have seen from the basic equations of flux of a component A is equal to C dAB dYA dx in the x direction plus YA n, where n is equal to for two component system Na plus Nb. So, this is equation number 1, and then we have seen the flux of A will be equal to Na by N C dAB between the two different points x 1 and x 2 will be this distance ln Na by N minus Ya 2 divided by Na by N minus Ya 1. So, this is equation number 2, and if we consider the case of diffusion of a particular component A through non-diffusing B, diffusing B component, that means the B is stagnant in that case, and also if we consider ideal gas mixture, ideal gas, in that case this C we can write P T total pressure by R T. So, that we can write the flux equation Na will be dAB Pt by RT x 2 minus x 1 ln Pt minus Pa 2 by Pt minus Pa 1, or which is we can write dAB Pt by RT x 2 minus x 1 into PBLM Pa 1 minus Pa 2, and this PBLM is equal to Pb 2 minus Pb 1, pressure difference between the 2 points, divided by ln Pb 2 by Pb 1. This is the partial pressure difference. So, this is the flux equations of a component A through non-diffusing B, and also we have seen the steady state equimolar counter diffusion. If between component A and B the diffusion is steady state, equimolar counter diffusion. So, in this case, for ideal gas, we have seen Na, the flux is equal to dAB by RT x2 minus x1 into the partial pressure difference PA1 minus PA2. So, these are the quick review of our previous class, where we have considered the diffusion is occurring through the constant area of the system. So, today we will also discuss the steady state molecular diffusion in fluids. As we said, this has two separate classifications. One is through constant area and this is through variable area. So, now consider steady state molecular diffusion of component A through equilateral triangle, which is uniformly tapered, equilateral triangle, where the diffusion, this is point 1, from this plane it is diffusing to point A2, where the Na cap is the diffusion rate of component A and the cross sectional area is varying along the length of the conduit. If we consider this is point 1 and this is point 2, the length of the side of the triangle is A1 at point 1 and A2 at point 2. So, the relations between this side of the triangle, which is gradually increasing from the left hand to the right hand, we can write. So, area will be half into side into altitude. So, which is equal to, if side is A, it will be A into height will be, for equilateral triangle it will be root 3 by 2 A. So, it will be root 3 by 4 A square. Now, if we return back to the Fick's law, diffusion of A through non-diffusing B. So, in this case, the governing equations of the flux Na into 1 minus partial pressure of A by Pt total pressure is equal to minus dAB by RT dPA by dx for ideal gas. Now, if we consider Na is the molar flux, so Na is equal to Na cap by area, which is equal to 4 by, if we substitute area over here, 4 by root 3 Na cap by A square, and if we substitute this one over here Na, so it will be minus RT by DAB into 4 Na cap divided by root 3 A square dx will be equal to PT total pressure into dPA partial pressure of A divided by PT minus PA. So, before we integrate these equations, we have to impose the limit where A is function of x. Since A is function of A, the size of the triangle will continuously change. So, we can have the relation A will be A1 at point 1 plus A2 minus A1 by x2 minus x1 into x minus x1. So, this is the relations how A is changing with x for the equilateral triangular shape. So, in this case we can write this will be A1 plus A2 minus A1 by x2 minus x1 into x minus A2 minus A1 by x2 minus x1 into x1. Now, if we differentiate, this will be dA dx. So, since this is constant, so this will be 0 plus A2 minus A1 into x2 minus x1 into 1 minus A2 minus A1 by x2 minus x1 into 0. So, this will be A2 minus A1 by x2 minus x1. So, we can write dA by dx is this. So, dx we can write x2 minus x1 divided by A2 minus A1 dA. So, if we substitute in our previous relation, say this is equation 1, if we substitute here the relations between A and x in this limit, we can have RT by DAB NA cap x2 minus x1 by A2 minus A1 integral A1 to A2 4 by root 3 A square dA, which is equal to PT integral partial pressure of A at point 1, partial pressure of A at point 2 dPA by PT minus PA. If we integrate, we can get minus RT NA cap by DAB into x2 minus x1 by a2 minus a1 into 4 by root 3, and this integration of this will be minus 1 by a with the limit a1 to a2 will be equal to minus pt into ln pt minus pa into, and the limit is pa1 to pa2. So, if we simplify this one, then we will have 4 minus 4 RT Na cap by root 3 DAB into x2 minus x1 by a2 minus a1 into 1 by a1 minus 1 by a2. So, will be equal to Pt ln Pt minus Pa1 by Pt minus Pa2. Na cap is the diffusion rate, will be equal to root over 3 DAB into Pt by 4 RT into a2 minus a1 will cancel out. So, it will be a1 a2 by x2 minus x1 ln Pt minus Pa1 by Pt minus Pa2. So, this is the molar flow rate equations of component A through the variable area of equilateral triangular cross section. If we consider a simple example like we considered before, the CO2 is diffusing through non-diffusing nitrogen at steady state in conduit of 2 meter long and at 300 Kelvin and 1 atmosphere pressure, and the partial pressure at the left end is 20 kilopascal and at the right end is 5 kilopascal. The cross section of the conduit is equilateral triangle of side 0.025 meter at the left end and tapering uniformly to 0.05 meter at the right end. So, we have to calculate the rate of transport of CO2 and the diffusivity between A and B, that is CO2 into through nitrogen is given 2 into 10 to the power minus 5 meter square per second. So, now let us consider the value which are given. The diffusion coefficient of CO2 into nitrogen is given as 2 into 10 to the power minus 5 meter square per second. R is known to us 8314 meter cube Pascal by K mole Kelvin. T, the temperature of the system is 300 K. Pressure Pt is given is 1 atmosphere, which is equal to 101.3 kilopascal, is equal to 101.3 into 10 to the power 3 Pascal. Partial pressure PA1 is given is 5 kilopascal, which is 5 into 10 to the power 3 Pascal. PA2 is also given 20 kilopascal, which is 20 into 10 to the power 3 Pascal, and the A1 is 0.025 meter, A2 0.05 meter. The side of the triangle and the distance x2 minus x1 is given as 2 meter. So, now if we substitute the value which are given, N A cap will be root 3 DAB PT by 4 RT A1 A2 by x2 minus x1 ln PT minus PA1 by PT minus PA2. So, if we substitute the values, which is root 3 into 2 into 10 to the power minus 5 meter square per second into 101.3 into 10 to the power 3 Pascal total pressure, and then into the A1 A2, which is 0.025 meter into 0.05 meter, this divided by 4 into 8314 meter cube Pascal divided by K mole Kelvin, temperature 300 Kelvin into 2 meter multiplied by ln 101.3 into 10 to the power 3 Pascal minus 5 into 10 to the power 3 Pascal divided by 101.3 10 to the power 3 Pascal total pressure minus 20 into 10 to the power 3 Pascal. So, if we solve, this is equal to 3.75 into 10 to the power minus 11 K mole per second. So, if we look into the unit balance, the pressure term will cancelled, this will cancelled out and Kelvin will cancel. So, you will have kilomole per second. So, this is the molar flow rate or of component A through non-diffusing B. Let us consider another example. The evaporation of a drop of liquids occurs and area continuously gets changed, or if we have a naphthalene ball and diameter of the ball is reduced, and certainly the area and flux gets changed. So, we will consider this where at point 1 the partial pressure is PA1, at point 2 partial pressure of component A is P2, and the radius is changing. So, the initial radius is R A 1, this is on the surface of the ball. So, if we apply the Fick's law of diffusion, consider the case diffusion of A through non-diffusing to B. So, in this case we know the flux is related with the partial pressure P A by P T, the total pressure is equal to minus D A B R T d P A d R for ideal gas. N A, you can write the flux N A cap by 4 pi r square, which is the area. So, now we can have the relation between these two. We can substitute this N A over here. So, we will essentially have minus R T N A cap by 4 pi d A B d R by R square is equal to P T d P A by P T minus P A. So, now if we include the limit, partial pressure of A 1 at R A R 1 and partial pressure of P A 2 at R 2, if we include this limit and integrate this equation, this will be minus R T N A cap by 4 pi d A B into P T 1 by R 1 minus 1 by R 2 is equal to ln P T minus P A 2 by P T minus P A 1. So, if we consider R 1 is very less than R 2, then 1 by R 2 approximately equal to 0. So, if we substitute this, then N A cap is equal to D A B P T by R T P B L M into R 1 P A 1 minus P A 2, this divided by 4 pi R 1 square. So, this is nothing but N A 1. N A 1 is the flux at the surface. Now, let us have an example. A sphere of naphthalene ball having a radius of 5 millimeter is suspended in a large volume of still air at 310 Kelvin and 1 atmosphere pressure. The partial pressure at the surface of naphthalene at 300 K is 50 Pascal. Assume dilute gas phase. So, and the DAB of naphthalene in air at 300 Kelvin is given 6 into 10 to the power minus 6 meter square per second. to calculate the rate of evaporation of naphthalene from the surface. Now, the data which are given is D A B is 6 into 10 to the power minus 6 meter square per second. Partial pressure P A 1 is given is 50 Pascal. P A 2 we can, since this is large volume of air, we can consider approximately equal to 0 for large volume of air, and R 1 is given is 5 millimeter, which is 5 into 10 to the power minus 3 meter, equal to 5 into this, and R is known to us. R is 8314 meter cube Pascal by K mole Kelvin. T is given 310 Kelvin, and PBLM, since it is very dilute solution, we can consider as PT total pressure, which is equal to 1 atmosphere is equal to 1.013 into 10 to the power 5 Pascal. So, now if we substitute these values in our governing equations, flux Na cap by 4 pi R 1 square will be equal to DAB PT by RT PBLM into R 1 into the partial pressure difference P A 1 minus P A 2. So, P A 1 is 50, which is given, and P A 2 is 0, we are assuming for large volume of air. So, if we substitute that values, which is 6 into 10 to the power minus 6 meter square per second, P T is 1.013 into 10 to the power 5 Pascal into 50 Pascal minus 0 divided by 8314 into 310 into 1013 into 10 to the power 5 into 5 into 10 to the power minus 3. This is meter, this is Pascal, and this is Kelvin, and this is meter cube Pascal K mole Kelvin. So, now after substitution of these, we will have this is 2.023 into 10 to the power minus 6 K mole per meter square second. Now, we will consider steady state molecular diffusion through another geometry, which is uniformly tapered, cylindrical in nature, and at point 1 the radius of the cylinder is R 1, and at point 2 the radius is R 2. In this case, we will consider steady state equimolar counter diffusion. Steady state equimolar counter diffusion. As we know, the flux is minus C dAB dYA dx plus YAN. So, for equimolar counter diffusion, and if we consider ideal gas, then this will be minus dAB PT by RT dYA by dx plus YAN. Now, for two component system and equimolar counter diffusion, Na will be minus Nb and N is Na plus Nb, and which is equal to 0. So, then this term will be 0 and we have the flux Na will be minus dAB by RT to dPA dx, and also Na we can write Na cap by pi r square, and this is equal to minus dAB by RT dPA by dx. If we use the geometry, then we can have a relations between R is equal to R2 minus R1 by x2 minus x1 x plus R1. So, this is the change of radius along the distance, along the length of the cylinder. We can replace this R in these equations and we can then differentiate. So, it will be Na cap by pi integral x1 to x2 dx by R2 minus R1 by x2 minus x1 into x by R1 square is equal to minus dAB by RT integral PA1 PA2 dPA. If we integrate with the limit at x is equal to 0, PA1 at x is equal to L, PA is PA2. So, if we integrate this with the limits, it will be Na cap will be dAB by RT into pi R1 R2 by L into PA1 minus PA2. Like earlier example, for equilateral triangle, we can integrate in similar way and we will have this diffusion rate equations of component A. Now, let us consider these examples where carbon dioxide is diffusing steady state through nitrogen by equimolar counter diffusion in the similar conduit of 2 meter length at 300 Kelvin and at 1 atmosphere pressure. The partial pressure at the left end is 20 kilopascal and 5 kilopascal at the other end. The cross section of the conduit is in the shape of cylindrical of radius 0.025 meter, and at the other end the radius is 0.05 meter. We have to calculate the molar flow rate of CO2 and the diffusion coefficient is given. If we substitute in these equations, Na cap is dAB by RT pi R1 R2 by L Pa2 minus Pa1. So, the value is given 2 into 10 to the power minus 5 meter square per second into 3.14 into 0.025 meter into 0.05 meter divided by 8314 meter cube Pascal by K mole Kelvin into 300 K into 2 meter multiplied by 20 into 10 to the power 3 Pascal minus 5 into 10 to the power 3 Pascal. So, this will be equal to 7.87 into 10 to the power minus 10 K mole per second. So, this is end of lecture 5, and in the next class we will consider the diffusion coefficient measurements. We will first consider the measurement of the diffusion coefficient in the gas phase, and then for the liquid phase, and then diffusion in solid phase. Thank you.